Welcome back to another video lesson for MAT 182 Trigonometry. In this lesson, we're going to build on the simplifying skills from lesson 12, and we're going to use those skills to verify trigonometric identities. So a trigonometric identity is simply an equation that is true for all values. So as you can see, we've got the identity cosine tangent equals sine. And the way we're going to do this is we're going to pick what we deem is the more complex side, and we're going to do our best to simplify that expression until it's equal to the expression on the right. So in this case, we've got cosine, which doesn't really simplify, and we've got tangent, which we can rewrite as sine over cosine. Now, when you're verifying an identity, the structure is really important. You don't want to skip any substitutions, and you want to carry along your equations so that each one is a copy of the one before it. So we're basically establishing a proof by saying each equation is equivalent to the one above. From here, we've got our cosines that will cancel, and this proof is done. Sine theta is equal to sine theta has been verified as true. This is the skill we're looking for. Of course, I am going to give us some more complicated examples. Let's take a look at the next one. Verify the identity sine theta cosecant theta minus cosine squared theta equals sine squared theta. So if we're determining which side is more complex, we're going to go with the left-hand side. We have two terms, and one of which is squared. When you see a squared, it's either going to be a Pythagorean identity or a factoring problem. For the most part, Pythagorean identities are going to be a better strategy. Sine theta, cosecant theta. This can be replaced with sine theta times 1 over sine theta. And we want to try to do one step at a time so that if we were justifying our scratch work, we could explain what replacement was happening in every step. And so my reasoning, if I was asked to provide reasoning, and yes, you probably will be asked to provide reasoning, I would say reciprocal identity. Algebraic simplification doesn't have to be justified. I want to see it as your instructor, but for the most part in a true proof, the algebraic is kind of done behind the scenes. So it's assumed if you're reading a proof that you know sine theta times 1 over sine theta simplifies to be 1. From here, we're actually looking square at a Pythagorean identity. Now I have some words of caution. When you're verifying an identity, you don't want to treat it like an algebraic equation, meaning I don't want to add the cosine to the other side. That's not what we're looking for. We want to stick to one side of the expression and make substitutions until that side is equivalent to the other side. So 1 minus cosine squared. Let's look back to the Pythagorean identities from the last lesson. We had an identity that was sine squared plus cosine squared is equal to 1. So like we saw in the last lesson, if we just subtract the cosine squared, we get sine squared theta is equal to 1 minus cosine squared theta. And this is the substitution that we can make in our problem. So the next step is sine squared equals sine squared, and we have verified this identity. If we were putting justification, we would say Pythagorean as our reasoning. Okay, from here, if you're ever asked to verify an identity, it's important to understand that not all equations are actually identities. So I'm going to pause the video, open up Desmos, and show you how to graph this equation to verify that it's true. Okay, we're back, and this time we're in Desmos, and what I'm going to do is type in the left side of the expression, which was sine times cosecant, and I'm using x, but you could use t or theta or anything like that, and it was minus cosine squared x, and that's giving me an error. Why? Let's try that again. cosine squared x. Okay, that works. And then negative, and then that must be the problem. Something's wrong with doing times cosecant x. If you look, I'll scroll over so you can see the whole view of the window. We're going to go ahead and type in the right side. And what I like about Desmos is that it defaults to a different color for each equation, so you can truly see that overlap. So the right-hand side of the expression was equal to sine squared x. And if the identity can be verified, if the identity is true, you will see perfect overlap between the two graphs. And so this is an example of a verifiable true identity. And that makes sense because when we were working on it on our paper, we were getting that it worked. So let's continue with the next example. From now on, you want to check if the identity is verifiable before you get into your proof. So for example 3, we're going to sines and cosines, the left-hand side of the problem. So let's rewrite cosecant theta minus cotangent theta equals sine theta over 1 plus cosine theta. Here we go. I have cosecant theta, which is equal to 1 over sine theta. This is a reciprocal identity. And then I have cotangent is cosine theta over sine theta, which is usually referred to as a quotient identity. And then I'm going to use a shortcut to carry down my right-hand side. From here, I actually have a common denominator, so I'm going to go ahead and combine these into a single fraction. Here is where I need the conjugate. So as you can see, the 1 minus cosine, that cosine's not squared. So I can't just replace that with a sine squared. This is not exactly a Pythagorean identity. When this happens and you see a binomial, so two terms with a plus or minus sign, you want to use the conjugate of that binomial, which in this case is 1 plus cosine theta. And we're going to go back to our algebra skills from 120, 150, or the last time you took an algebra or pre-calc class. And we are going to distribute and simplify this expression. So in the numerator, if I use distributive property, all four terms, don't forget to make sure you do all four, I get 1 minus cosine theta plus cosine theta minus cosine squared theta. And the denominator is not a conjugate, so you do not want to distribute these. You want to leave them as separate factors because separate factors are going to give you a chance to simplify the expression. Again, I'm running out of room in this problem. This sort of algebra, so this distributive property you see, would normally be done on the sidelines or behind the scenes of a proof. You wouldn't show this anywhere in your actual proof. You would just jump from 1 minus cosine theta over sine theta to the next step, which, let me switch colors, after you delete these terms because they cancel, would be 1 minus cosine squared theta over 1 plus cosine theta sine theta. So let's go ahead and continue this in the space I reserved on the other side. 1 minus cosine squared theta over 1 plus cosine theta times sine theta. The numerator is a Pythagorean identity. So 1 minus cosine squared theta can be replaced with sine squared theta, which is now our third time seeing this in the notes. Leave the 1 plus cosine theta alone. And keep in mind, if you look at your goal, we want a 1 plus cosine theta in the denominator because that's what we have on the right-hand side. So once we get that in the denominator, we know we're on the right track. Finally, we have a sine theta in the numerator and denominator, and those can cancel. So our final equation is that sine theta over 1 plus cosine theta is equal to sine theta over 1 plus cosine theta. If you're doing this work to be submitted, you don't want to take shortcuts like drawing this arrow. You want to write the right-hand side each time. And this will remind you of your goal when you're doing the proof, which is to get the left hand and right hand sides equal to each other. All right, let's get down to the last example, which is example 5. And I actually did not leave a lot of space to do this, so hopefully we can get through this. In this last example, we're looking at the type of problem a highly proficient student would be able to simplify. And I'm hoping you can tell by looking at this 2b or 2 beta, this is not going to be one of the fundamental or Pythagorean theorem identities. This is actually one of the double angle identities that we took notes on before we went on spring break. So if you're looking at your formula sheet or a list of the identities, so I'm going to pause and I'm going to do a Google image search on trigonometric identities. Okay, so a quick Google image search, just trigonometric identities, go straight for the images. You can see the addition and subtraction, double angle, half angle, and we're focused on these double angle identities. So let's pull these up and get a nice zoom going. Why does it look like it's getting smaller? Okay, anyway, so from here, we can see that sine 2 theta can be replaced with 2 sine theta cosine theta, and that for cosine 2 theta, we actually have 3 options for replacing. And so when you're writing a verifying a trigonometric identity, you really might have to try all 3 of these, but we want to do a little pre-thinking, maybe make a plan as to which one we're going to use that can be specific, okay? So let's get back to our example right here. So cosine 2 beta, we have 3 options. Minus sine 2 beta, we don't. We only have 1 option. But I would like to point out that our goal is to have 2 sine 2 beta, and we already have 1 sine 2 beta. We also have a goal of having 1 minus 2 sine 2 beta. And so we're going to look for a way to replace the cosine 2 beta that's going to give us this option, okay? So let's start with one of the most similar options, which is going to be 1 minus 2 sine squared theta. Sorry, beta, not theta. And that equals 1 minus 2 sine 2 beta. From here, we're looking for a way to rewrite this expression. Maybe we can replace the sine squared beta with 1 minus cosine squared. Maybe we can factor. Or maybe we're just stuck. So one thing I wanted to remind you is that before you verify an identity, especially if it doesn't say verify the identity, you might want to check that it actually works. Let's hop on over to Desmos and type in the left-hand side of the equation and the right-hand side of the equation to make sure that they're actually equal. And so I've done that. Oh, there's a typo. And it turns out that these aren't equal, and so this is not an identity and cannot be verified. Thank you for watching the second lesson on verifying trigonometric identities. There is an assignment, it's quite long, that gives you a large variety of identities to try and verify. For submission, I'm going to be selecting a random order of questions, and I would like you to submit the proof for each of those randomly selected problems through Canvas.